Muted.
Thank you very much, Courtney, and I appreciate the invitation to join the First Friday webinar series. I am the lightweight fill specialist for Erics Industries, and before we get started, I'd like to tell you a little bit more about me. I have been involved in lightweight fills since the early 90s. I started off my career as a lightweight fill specialist with expanded polystyrene geofoam blocks, and since then have transitioned to cellular concrete as it addresses a number of the issues that one encounters with expanded polystyrene blocks. I think it's important to remember when taking a look at cellular concrete that it is not designed to be the wearing surface of the project, but rather designed to replace traditionally compacted backfill. The picture you're seeing presently is sort of how you typically would place cellular concrete in a open void space scenario, and it is self-leveling and self-compacting. Cellular concrete has been around for quite a while. It started off in the early 1900s in Sweden, and it really started taking traction right after World War II. Back then, we were basically utilizing a protein-based material. Today, we're also utilizing hybrid materials or synthetic materials, and combining the two and having hybrids between the protein and synthetic, depending on what we're trying to achieve with it. And then beyond the hybrid materials, we are also have a pervious version available, so that we have both open cell and closed cell technologies available for the placement of cellular concrete. I think I would like to start off by reviewing the definition of cellular concrete under the ACI 523, which is a material that is a mixture of cement, water, and preformed foam, and a key element that is under 50 pounds per cubic foot. Erics Industries does not get involved in the installation of the materials, get involved in the manufacturing of the foam portion. So we do the chemistry of the air bubble. Every concentrated gallon of concentrated liquid will produce anywhere between 110 to 220 cubic feet of foam. So it's a tremendous amount of foam all the way. Under the ASTM standards, we're looking at two types of foaming agents. We've got the preformed foam, and then we have the agitated foam, which you're probably more familiar with because that is the flowable fill under ACI 229. Now, I'll confuse the issue a little bit more here, because a preformed foam can be a flowable fill, but a flowable fill cannot be a cellular concrete, and that is purely by definition, because again, the preformed foam is under 50 pounds per cubic foot. So I'll repeat that one more time. A cellular concrete can be a flowable fill, but a flowable fill cannot be a cellular concrete. And again, that's purely by definition. Today, I'm going to spend most of the 45 minutes here on the ACI 523, which is under 50 pounds per cubic foot. When looking at the mixture of cement, water, and foam, the foam portion or the air bubble literally translates and replaces the aggregate in the mixture. So we place it as a liquid, but we calculate it out as a solid, and it becomes very flexible and has a tremendous amount of options available for you with this cellular concrete. When you look at a sample of cellular concrete, you will see a tremendous amount of void spaces, and those void spaces are the dissipated leftover bubbles within the material. As I mentioned to you a little bit ago, we will be reviewing both a pervious and a non-pervious options throughout the presentation. I'll start off the presentation mostly focusing in on a non-pervious, but there's an awful lot of pervious opportunities as well. So we'll be talking both about the open and closed cell materials. The placement of cellular concrete in the most simplistic manner is where we take a neat cement mix or a cement water mix in a ready mix trucks. We can turn around and put that through a pumper and then expand the concentrated foaming agent out through a foaming generator. And depending on the mixture and the recipe that we do, we'll then blend it together. Throughout the country, there are three basic types of installers. The various installers that do high production are completely mobilized, and there's a handful of them around the country. These individuals will place anywhere between 125 to 300 cubic yards per hour. Then there are those installers that have mobile mixing units, and those individuals will place anywhere between 75 and 125 cubic yards an hour. And then there are those that work with the ready mix operators, and they will literally place yards at a time. So depending on your project that you're working on will really determine and depend what type of an installer you would be looking for your project. So if one calls me up and says, well, I need a specific volume requirement, that'll sort of determine on who we would recommend to place the material. Cellular concrete is extremely effective on the carbon footprint on the project because it requires a lot less equipment on the project because the material is self-compacting and self-leveling. So you're reducing a tremendous amount of the equipment, reducing the fuel utilization, and also reducing the manpower involved with the placement of the material. As I mentioned before with the cellular concrete, it is not designed to be the wearing surface of the project. Cellular concrete replaces traditionally compacted backfill. So if we take a look at traditionally compacted backfill at what, 50, 80 PSI, and if we compare that, for example, to a 30 pound per cubic foot scenario, that material will give us 140 PSI. So we are well ahead of the game. So traditionally compacted backfill being what, maybe 110, 120 pounds per cubic foot versus the cellular concrete at 30 pounds per cubic foot, giving a high compressive strength than we normally would get from traditionally compacted backfill. A 30 pound per cubic foot scenario, when looking at it, will give you about 75% air structure within the material. And that's what makes it lightweight. So with the cellular concrete, as you go up in density, you will obviously go up in the compressive strength. But I will always challenge you of why you want to go with a higher PSI when you're replacing traditionally compacted backfill material, because it will drive up the cost of the material. I'm not going to spend a lot of time on the ASTM standards for cellular concrete, but they are in place and they are written in the various specifications out there. It's the ASTM standards for the foaming agents, how to place the material, and how to test for the compressive strength on the job site. All QA, QC is always done out in the field, because that is ultimately where we pull that recipe together of mixing the cement, water, and foam. I need to talk a little bit about bubble structure because of some of the things that we are doing with the bubbles today. We had Artem and Associates do a study to where we filled a clear cylinder with a very fresh cement water foam mixture. We filled it up to 12 inches, put it under some pressure, compressed that material down to 9 inches on the fresh cement water slurry, held it there for a short period of time, and then released it. Upon its release, it bounced back to its original 12 inches that was originally placed in there. And what that shows you is that the cellular concrete truly has a flexible bubble in there, and that the bubble has got the elasticity required to do some of the unique things that we are doing with the material. If we are taking a look at what we have traditionally done with cellular concrete, we have pumped the material for 3 to 3 foot lifts. We have pumped it for a distance of 5,000 feet. Permeability was not an option. Viscosity was almost one. And we had limited utilization of fly ash. If we take a look at what we are doing today with the cellular concrete and with the bubble structures out there, we are now doing lifts in the tune of 4 to 20 feet in height. We actually just had an installer in Texas do a void fill scenario that was in the shape of a funnel that was 2 feet diameter to bottom, flaring up to 25 feet at the top, and was a total of a 35-foot height void at a bridge abutments, which they filled up in one lift. And when it came back the next morning, there was less than a ½ an inch drop in the overall material. So we're getting tremendous lift heights with the bubble structure and not losing the bubble structure. We have now pumped this material for over 14,000 feet. We just had an installer in Hawaii work on a tunnel that I'll share with you in a little bit that pumped the material just shy of 3 miles, just over 15,000 feet. So if you think about that, when taking the material through a 3-inch or 4-inch hose and pumping it for distances, you can offset your batch mixing equipment in a distance and then lead into the job site with a 3 or 4-inch hose and eliminate a lot of safety aspects within the job site and remove a lot of traffic away from the job site as well. Permeability is an option, and I'll spend some more time on that. We can pump a much thicker sludge than we could in the past as well. And we have much greater utilization of fly ash and slag cement. When looking at the various geotechnical applications, there are a vast majority of the industries that we get involved in is in the mining industry, abandoning mines, and that obviously leads us into the tunneling and annular fill scenarios. When doing annular fills and tunnel backfills, it's extremely important to remember that the material, when being placed, it gets extremely fluid, so it will go into every nook and cranny that it can find. It's also important to remember that this material is pumped under extremely low pressures so that you will not run into a floating pipe or damaged lining, those slip lining projects. And the shrinkage of the material is less than 0.3%. So you've got a tremendous amount of advantages on various projects out there. I'm going to share with you some projects. From an annular fill and abandonment perspective, this was a project that was done in Maine. It was completed in less than a day, and it was 150 cubic yards of material, 500 psi material that was placed. As I just mentioned, the project in Hawaii, it's actually just been completed. It's a 13-foot tunnel that was relined with a 10-foot diameter pipe on the inside for a sewer treatment facility, and it's about just shy of a 3-mile long project out there for the annular fill. The material that was utilized in this project was 50 pound per cubic foot material. It was done through a 4-inch injection line. And the interesting thing was, from a heat hydration perspective, they actually utilized chilled water because the original water was 70 degrees and they chilled it down to 50 degrees. And in order to control some of that heat hydration over that whole distance, they maintained the lifts at 18 to 24-inch lifts. But again, the bubble quality becomes extremely important to be able to pump over that distance and not have a bubble loss. Another abandonment project that was done in Atlanta was the actual project on this gas pipeline abandonment is about 26 miles. They completed 12.5 miles of it, where they placed 40 PCF non-pervious material. And they have placement points every 1,000, 1,500 feet. This next picture I'd like to show is actually from an installer out of Australia. And it's a pipe abandonment project. And it clearly shows the fluidity of the material being placed during a utility abandonment project, filling up every nook and cranny that it can find. On another project that was done in Fayetteville, North Carolina, was a bridge abutment that had a small washout, and they replaced the backfill there with 900 cubic feet of cellular concrete that was used with the ready mix trucks. And the project duration was a total of 3 hours, so it was very, very short. Because you can literally take a ready mix truck and every cubic yard of a neat cement mix or a cement water mix, you can literally expand that out to about 3.7 times its volume with the foam. It always behooves one to show a picture of one's boss on a project. So this was at one of the boroughs in New York City, abandoning an old drawbridge. And the drawbridge counterweight well pit had to be abandoned. It was 29 feet in total depth. It was done in 4-foot lifts. And the reason it was done in 4-foot lifts is because of the vibrations involved in that whole area. This project was right next to Amtrak, running consistently with 2 major highways right over it and alongside of it as well, with heavy tractor trailer traffic, giving a tremendous amount of vibration. And the installer wanted to make sure that he didn't run into a bubble collapse. From another abandonment scenario, this was an indoor pool that was being abandoned from an old therapeutic center, and the installer had to fill it in there before the final slab was placed over it to the conversion of a new office building. Personally, I would have kept the pool in my new office, but they decided to abandon it. When you're doing pools, Don't it's with the utilization of the cellular concrete, it's a great aspect to backfill with it. Just a reminder that when you're doing that scenario, make sure that you fill the water in the pool at the same rate, so you don't have a collapse there. Another opportunity one has with the utilization of cellular concrete is to bring the subgrade to just below the final slab. And when you're doing that, you're saving a tremendous amount of labor, but you're also encapsulating any utilities that might be going through it. On another project, from backfilling from rough grade to the top of the footing, it's a project that was done in California, actually, and there's no compaction requirements, and you have a tremendous amount of reduced traffic involved in the project, and you're bringing everything up to grade, self-leveling, and self-compacting. From a subgrade modification, I prefer to call it soft soil remediation, I guess. Anytime you create a large monolithic block of cellular concrete, you're going to have a tremendous advantage, especially during seismic activity, because of your lightweight fills there. And if you run that through your FLAC numerical modeling program, you will automatically see a huge advantage of the lightweight fills versus traditionally compacted backfills. The material will also have an insulating factor. So when you're going from and transitioning from your native soils to your cellular concrete, you want to make sure that if you're doing, like, for example, a bridge approach, that you take a look at your icing differential, and you may have to adjust your total pavement surface accordingly. I'll go back to this one here just for a minute here. Every once in a while, we'll see the partitioning off of segments on projects from the installer's perspective. The reason that they partition it off either with a geomembrane or plywood or whatever it is on hand is because installers like to be able to calculate out the volume being placed on a daily basis. And some of it has to do with heat hydration, but mostly these installers like to get paid. So we'll see the partitioning off of various segments. When it comes to working with soft soil scenarios and unstable soils, again, from a labor perspective, the mixing equipment can be offset off-site, as you can see here at the University of Connecticut. And the 3-inch hose leading into the project with the placement. The labor force involved with the placement of cellular concrete is very minimal. You generally have somebody at the nozzle of the hose. You have an individual assisting moving the hose around. And then you've got 1 or 2 individuals in the mixing facility to receive materials and doing the actual mix and making sure that the appropriate amount of material is being placed. In this case, we're placing 150 cubic yards an hour, but it really makes no difference whether you're placing 150 cubic yards an hour or 75 or 300 cubic yards an hour, because at that point it's all within the equipment. On the project that was done in, actually it's Orlando, just northwest of Orlando, is soft soil remediation, where they wanted to lighten up the load on a road widening project in the marshy area. They drove the sheet pile walls and then tied those back into a retaining structure, and then did the backfill. It was 3,000 cubic yards. They utilized ready mix trucks on that, and they completed that project and the backfill in 2.5 evenings. And it was done during the evening to make sure that there was no ready mix trucks during the heavy traffic hours. I'll get back to vertical retaining structures here in a minute, because that driven sheet pile wall is actually a little bit over engineered, and I'll show you why here in a minute. When you're talking about soft soil remediation, that obviously brings us into the levee applications as well, because if you take a look at what we traditionally do with levees, we add more native soils upon a levee to increase its overall elevation, and then we have more weight, so we have more settlement. Consider lightening up the load within the core of the levee, and then place the appropriate amount of overburden upon the lightweight core to make sure that you counteract any buoyancy issue that you might encounter. Since we're talking about buoyancy, that brings us into the TREMI applications. Anytime we do TREMI applications, we have to displace water, and we will have to go with at least 65, 70 pound per cubic foot material to displace the water on a project. Having said that, if I can dewater a site, I would prefer to dewater it, place a lighter cellular concrete in its place, and make sure we have the appropriate amount of overburden to counteract any buoyancy concerns. The other option, I'll get back into that in a minute, would be to utilize a pervious cellular material to allow the infiltration of water to assist with the counteracting of the buoyancy factor of the material. But if you cannot dewater, you will have to TREMI the application with 65, 70 pounds per cubic foot material. When looking at various retaining structures with the utilization of cellular concrete, anytime you replace the sliding wedge of the soil and stay above the angular repose to create a vertical fascia wall, once the cellular concrete is cured, that vertical fascia wall will end up having a zero lateral load factor. The only time you're going to have a lateral load will be during the liquid phase of the cellular concrete. But once it's cured, you will end up having a zero lateral load factor as long as you've replaced the sliding wedge of the soil. Cellular concrete also works with a lot of different segmental walls throughout the country and throughout the world. 5-foot segmental walls, precast walls. When it comes to the strapping configurations, the original strap configuration totally changes with the utilization of cellular concrete, because the straps no longer are utilized for its original intent. They are now utilizing to hold that fascia wall in place to prevent it from falling forward. But that vertical fascia wall will end up having a zero lateral load factor. From the internal angle of friction perspective, if you're looking at from a conservative perspective, you're generally looking at 35 to 40 degrees. On a liberal side, you're looking at 60 to 70 degrees. The thing is that it really depends how you look at that wall. Are you looking and designing it as a soil wall, or are you looking and designing it as a concrete wall? So I could argue that either way for you, depending on how you want to take a look at it. Had to show you some local projects. This one case is Illinois DOT, who's a Lakeshore Drive and I-55 interchange. There's 6 phases over 2 years. 1,000 cubic yards a day of production was placed of lightweight 40 PSI material there. I think it's interesting to note in between you and the picture on the upper left-hand side is the taping that is done between those 5-foot segmental walls, because cellular concrete, when it's being placed, is extremely fluid and will seep through the various joints. Some of those straps in the bottom right-hand picture are a little bit longer than they really needed. A little bit over-engineered, but that's okay. When it comes to strapping configuration, Sometimes we see the straps within the lift, and sometimes we see the straps between the lifts. Your lift height obviously is going to be determined by your strap configuration one way or the other. I can argue your strap configuration either way, be it within the lift configuration or between lifts. If you take a look between lifts, if you take a look at the coefficient of friction, for example, between dirt and concrete, you're looking at 0.3, 0.5. If you look at the coefficient of friction, for example, between geofoam blocks, you're looking at about 0.6. Coefficient of friction between lifts of cellular concrete, you're probably looking at 0.75 to 0.85. Very, very high. So you're not going to run into a situation where you're going to have a strap pull out. On another project that was done for the Illinois DOT is the Circle Interchange. It was 18,000 cubic yards of cellular. Again, it was 40 PSI material and over four phases over 2-year duration. T-walls are starting to make more and more of an impact around the country. They're relatively big in the New England area on the West Coast, but thought I'd share that with you because the stems of the T-wall configuration are drastically reduced in length with the utilization of cellular concrete. The other thing you will note is that as this material is being placed, a great picture and a great shot to show how the material is self-leveling when being placed on a project. A lot of times I get asked, well, what is my overall height limitation with the utilization of a cellular concrete material? There really is no height limitation from a cellular concrete vertical fascia wall. The limitation is going to be a height-width relationship to wind overtopping, which is your true height limitation. In this case, this picture in Bellingham, Washington, is a double bridge abutment, solid cellular concrete material in excess of 50 feet in height and having placed shotcrete over the vertical fascia walls. This was done actually in 2-foot lifts in order to create the mesh baskets that ultimately assisted with the placement of the shotcrete. When it comes to underground utilities and the placement of the cellular concrete with those, your trench configuration for utilities is drastically reduced in width because all we need to get the cellular concrete into the hunch areas of the utility is we do not need more than 6 inches on either side of that utility to get into the hunch areas to make sure we have the appropriate compaction. Again, the material is self-compacting, self-leveling. And no compaction is required, no vibrating rods either, and it will fill every nook and cranny within the project. Because you're going with a much narrower trench than you normally would go, you're also saving some money on that. And in some cases, you might be able to reduce your right-of-way scenarios on your project. Cellular concrete has an insulating factor because of that air bubble. Anytime you place a slab of cellular concrete over existing or buried utilities, you will insulate those utilities. So as your frost line drops in the ground, it will insulate those utilities. I'm seeing more and more utilities and municipalities being identified with dye. Dye and cellular concrete is extremely cheap and is a great insurance factor that as future operations occur on various projects, that as soon as the colored dye is hit, people know that there's something buried there. This is a water main abandonment at the Illinois tollways. It was value engineered from flowable fill. And you can see that the hose that was led from the staging area to the various injection points was just over 1,000 feet. But again, the staging area is offset on the project, eliminating the traffic involved. I'm sorry, I hit the wrong button on there. Let me go back here a second, and I apologize on that. Let me, bear with me here, I'm getting there. I do apologize for that. I hit the wrong button in my excitement of cellular concrete. The material is fully excavatable and extremely versatile. Again, we're talking lightweight fill materials replacing traditionally compacted backfill. To get a nice clean edge on the material and the cut, you will need a concrete saw. If you do not use a concrete saw, you will end up with a ragged edge upon the material. Pervious cellular concrete is extremely pervious on that. The permeability on pervious cellular concrete starts at 162 centimeters per hour. The video that you're seeing now is one that I use at a lot of presentations around the country where I am just pouring water through a sample block of pervious cellular concrete. The difference between pervious cellular concrete and non-pervious cellular concrete is within the chemistry of the air bubbles. When it comes to the non-pervious cellular concrete, we want to maintain the structure of that air bubble, where with the pervious cellular concrete, we want those bubbles to coalesce or unite to create open cell technology. Your concrete water foam mixed designs are going to be identically the same. The only difference will be the chemistry of that air bubble. Pervious cellular concrete is used in an awful lot of different applications throughout the world. And the most famous one would be Citi Field, where the Mets play. And the Mets can never ever claim a wet ball field for not being able to play a game on a project, because the whole ball field, playing field sits on top of 4 feet of pervious cellular concrete, which sits on top of the organic clays, and then the playing field. I always recommend to people that when you've got native soils over pervious cellular concrete, use a silt fabric to maintain long-term permeability within the project. On another project that was done in North Dakota, these are actually the completed finished abutments. These abutments had continual settlement issues, and the maintenance department in Fargo did a great job over the years in controlling the settlement scenarios, because before they dug it out and everything else, they had placed over 3 feet of asphalt in the abutment areas. The pervious cellular concrete was placed along the abutments and eliminated the settlement concerns in that area by reducing the loading on the native soils. They utilized 2,600 cubic yards of 20 pound per cubic foot cellular material. At the New Orleans airport, which is literally built in the marsh, with the expansion program that they're doing there presently, they wanted to create a zero loading factor for the utility trucks around the new lighting vault building, which is going to house all the electrical factors of the New Orleans expansion that they're doing with the runways, taxiways, and terminals. To create the zero loading factor in that area, they dug out 4 feet of muck, for lack of better words. They placed down a silt fabric and then replaced it with 4 feet of pervious cellular concrete, and then placing the crushed lime over top of that, and then the final pavement over that. Today, that project acts like a great big sponge because it sits right at the water table. So as the water table rises, it is absorbed into the pervious cellular concrete, and as the water table drops, it is released again. The Missouri DOT wanted to have a demonstration and live demonstration of the permeability of cellular concrete, and they asked an installer to dig a 4 foot deep test trench, fill it up with pervious cellular concrete, and they did that one afternoon. And the following morning, the Missouri DOT came out for a demonstration on permeability. And this was the demonstration that was observed for the Missouri DOT on the test trench. Pervious cellular concrete is extremely pervious. It starts at 162 centimeters an hour and goes up from there. Pervious cellular concrete and its permeability, we see the best permeability between 25 and 35 pounds per cubic foot. Once we increase the density on the pervious cellular concrete, we start losing that permeability. So that's why we generally see pervious cellular concrete placed between 25 35 pounds per cubic foot. The void structure within pervious cellular concrete is quite extreme, and was demonstrated by the University of Missouri at Kansas City. You will never ever fill 100% of those voids with water infiltration. I always suggest to people to consider 55% of the volume for water infiltration, but don't go above that, because you'll never fill up every void within the structure. So water infiltration, consider 55% of that volume can be utilized for water infiltration, which obviously helps with counteracting any buoyancy issues that you might encounter. Some questions have come up in reference to compressive strength with saturation of the pervious cellular concrete. Again, at the University of Missouri at Kansas City, some studies were done on both a dry pervious cellular concrete, partially saturated and fully saturated. I'm going to ask you to ignore the fully saturated material because that is truly under laboratory conditions and will never affect a true field conditions, because you're not going to be able to infiltrate 100% of those voids. So let's take, and those black lines on the graph demonstrate your minimum requirements as per the ASTM standards of compressive strength requirements. And in all cases, they exceed the minimum requirements. I got to tell you about an interesting project that we observed after the placement on the pervious cellular material on a sinkhole in Pennsylvania. And when we showed up 72 hours after the placement of pervious cellular material, we saw tracked equipment going directly over the pervious cellular material. Sort of interesting because obviously it was some scarification, but it was very much on the surface and really became a non-issue. So we were happy to see that in such a short period of time. In between lifts of cellular concrete, all we need is 1 PSI. We do the walkability test and we can put another lift. It generally occurs between 6 to 12 hours after the placement of a lift to place another one. And that is without an accelerant. Use an accelerant, that'll speed it up a little bit. We also get involved in green roof applications with the utilization of pervious and non-pervious cellular material. My definition of a green roof is a little bit different because I don't look at a green roof from just a flat green grass deck scenario, where I like to utilize pervious cellular material to create elevation changes. So on the right-hand side picture in the illustration, you'll see where you've got the roof deck, placing a waterproofing membrane over that, using the pervious cellular concrete to create various elevation changes, placing a silt fabric over the pervious cellular concrete, then my growing medium, and then either my pavers over my vegetation. So I've got different options out there, and I can always carve out the placement of various root balls requirements within the pervious cellular concrete. If I start off with a roof deck that doesn't have your traditional 1/4 inch per foot drain, you utilize your non-pervious cellular concrete to create that slope. Place your waterproofing membrane down on top of that, then utilize your pervious cellular concrete to create your elevation changes on your roof deck. Silt fabric over that, then your growing medium and your vegetational leading down to your roof drain. Just an option. It's very economical to do so and gives your client something else to think about. One more project I had to show you just came to my attention here not too long ago. That to share with you what some of the installers are doing around the country with cellular concrete. This was the placement of some cellular on a bridge approach where they had a 8% longitudinal slope and 12% cross slope with the cellular concrete. So the various applications throughout the world with the utilization of cellular concrete. We get involved in sound wall applications because that air bubble gives you sound attenuation as well. Housing applications. During the most recent election, when Vice President-elect at the time, Vice President-elect Pence's plane went off at the end of LaGuardia, it was stopped by cellular concrete as an arresting system at the end of the runway. Just another use out there. So if you take a look at the utilization of cellular concrete, you've got a tremendous amount of advantages for the utilization of cellular concrete on a multitude of different applications out there. And Courtney, if we're able to, we can throw it out and respond to some of the questions maybe.
Yes, absolutely. Sorry, give me just a second here. I've gotten one question so far, but if anyone has any other questions that they'd like to ask, please feel free to type those in. The first question that we received is, can cellular concrete be placed in cold weather?
Absolutely. We place cellular concrete in Alaska and up above the Arctic circles quite frequently. We like to place it at higher temperatures, but yes, cellular can be placed at very low temperatures. Sometimes we have to use and warm the water up a little bit and bring the temperature up on the water. Sometimes we have to use blankets, so we have to control the heat hydration at times, yes. Hopefully that answers your question.
And I have another question about what the costs are like.
What the cost is of cellular concrete. Somewhere along the line, I had a feeling that question might come up. I think it's important to remember that Arex Industries does not install material. So let me direct a little bit from a material cost perspective, because there's an awful lot of factors involved with the placement of cellular concrete. I'm trying to advance my slide here. I'll get there. All right, so if we take a look at material costs on a project, and if you take a look and do a Google search on the cost of cement, you will end up with about $128 per ton of cement. I value water at about $2 per 1,000 gallons. And the most expensive concentrate that's on the Arex price list is $85 a gallon concentrate. Again, remember that every gallon makes about 220 cubic feet of foam. So that's an awful lot of foam. So if we take a look at a recipe, for example, of a 30-pound per cubic foot scenario, we will end up using 512 pounds of cement, 36.2 gallons of water, and 20.3 cubic feet of foam in every cubic yard. So if you take a look at that recipe and apply those dollar factors to it on raw material costs before the cost of installation, you will end up about $40.81 a gallon. So having said that, you also heard me say earlier on that I will always drive down the density of the material because I will have an economic influence on the project. And here is why. If you compare a 20, 30, and 40 pound per cubic foot material, on a material cost alone, you will have a drastic influencing factor. Keep in mind, these are material costs only. They are not involving any site factors, number of mobilizations, type of equipment brought in, and those kind of things, and unique site scenarios. I will give you an extreme that I saw. It was downtown Manhattan on a very, very small project. And it was, I think it was, if I recall, about 10 cubic yards. And being downtown Manhattan, it was just shy of $1,500 a cubic yard. Having said that, on a very large project, I have seen it down placed as low as $38 a cubic yard. So that gives you sort of the range, and I hope that answers the pricing question.
Another question just came through. Would it be applicable to place cellular concrete in an abandoned mine between 100 and 300 feet below ground that is flooded? Interesting
you bring that up. We just finished a trial study with some ARX transport material because we are now moving mine tailings from point A to point B, displacing water altogether, using mine tailings up to 3/4 inch aggregate mixed with a foam and dropping it. And we're not doing it underwater as well. That's one way to take a look and consider doing that. The other thing to take a look at is doing a TREMI application when displacing the water. But at that point, you know, where's that water going to go in the abandoned mine? Hopefully that answers the question. And whoever asked that question, if you touch base with me, or send me an email, I can send you some more information on that as well. Before I forget to tell you, I will be sending Courtney a number of documents for distribution and a copy of the cellular concrete presentation. for your review. And if I miss anything, don't hesitate to touch base with me. Any other questions that are around, Courtney?
The only other question that I received is if you could go into a little more detail on the difference between permeability and infiltration.
Good question. I'm going to go back to that slide, if I may. So bear with me here just a second while I bring up that slide. I think I brought it up. And then for some reason I'm having trouble bringing up that one slide. But anyway, permeability, you're generally looking at anywhere from 162 centimeters per hour on up. Your infiltration is going to be slightly faster, obviously, in a lower density because you're going to have more air bubble structure within that with a greater void space. So your infiltration into the lower density pervious cellular material will be faster. And if you send me an email, I can actually send you the slides involved with the permeability and infiltration. Was there anything else, Courtney?
Nope, no other questions on my end. So with that, I would like to say thank you, Nico, very much for a great presentation. And just a reminder to everyone to complete the quiz and reach out if you have any questions. I will be sending out the supplementary materials from Nico probably later today or Monday at the latest. So I just want to, again, say thank you to Nico. Thank you to all of you who attended, and have a wonderful weekend.
Thank you, Courtney.
All right. Bye-bye, everybody.